Okay, so it's a great pleasure to have in today's Laboratory of the Science seminar uh, Umair Wani from University of New Mexico. Umair is a student in PhD student now, which is working in different problems, intersection between differential equation, fluid dynamics, data-driven dynamical systems, and in particular worked with me in the summer on some extension of sparse identification methods for governing equations when the underlying dynamics is on a compact Riemannian manifold. And today is going to talk a little bit about this problem. So thanks a lot, Omer, for being here. The stage is yours.
Thank you, Dr. Alessandro, for introducing me. So yeah, this is actually the project that we were working during the summers. So the project is actually about the SINDy algorithm, and we were actually looking for to extend this algorithm on the compact Riemannian manifolds. So this project is the presentation that I am presenting today is actually about the examples that we constructed while working on this project and the name. So let's actually move to the abstract. That what we have done is that we were exploring this SINDy algorithm, which the SINDy here stands for this sparse identification of nonlinear dynamic these nonlinear dynamical equations. And what we were trying to do is that we were trying to see whether we can extend these on the compact Riemann manifolds. Firstly, what we did was that we demonstrated it through, because there are actually not just one SINDy, there is the SINDy that what we call as the simple SINDy, and then we had the SINDy-PI, which is the extension of the simple SINDy. What we did was, in the beginning, we worked on some of the examples from the SINDy paper, which is actually the basic paper, and we actually reconstructed those examples. Next, what we saw was that this simple SINDy has some issues, and those issues actually I will actually explain during this talk. And what we did was, then we moved to SINDy-PI and we explored that method, and we constructed few examples or using that method. Then we moved to this SINDy-PI, and we were trying to develop some examples, or actually to develop actually the general algorithm which can actually capture the dynamics of if the data is on the compact Riemannian manifolds. So the talk is actually about that, where we have constructed the examples for the simple SINDys, then about the SINDy-PI, and then we moved to SINDy-PI on the compact Riemannian manifolds. So let me start here. So this is actually the introduction to the SINDy algorithm. So this is actually the sparse identification of nonlinear dynamics, where we have the data, and from that data we want to capture the dynamics, like what was the dynamics behind that data, or from which dynamics, like where we have got this data. So the idea is that we have the data and we want to get the equations, and so that is actually the basic idea. And what we want to do is, and since the name says that this is a sparse identification, so the idea is that we know that we can actually define any system using number of equations, number of variables, but what we want to do is that we want to use the least number of variables, so that the dynamics that we will get, so that should be like is so it should be we can, so that we can understand it in a much easier way, because if we have a lesser number of variables, obviously we can understand the dynamics very easily. And that is actually the idea, like we have the data, we want to get the equations, but in those equations what we should have the least number of variables that are actually governing that dynamics. So then the thing is, like, how it works is that, suppose for any system, this is actually the dynamical system we have. So suppose this, for any dynamical system, we usually have this, the equation is like where we have this x dot on the left, which is actually the differential equation that is actually representing the system, and on the right we have this f function. And the sparse, this SINDy, what it does is it is trying to replicate this f here. So what we are trying to do is that from the data we want to construct this f using that data. And to determine that f, what we do is that we have this, since we have this data, what we do is that we construct the matrix using the time series data x, and from that x then we construct this x dot. That is actually the first step. What we do is that we constructed these matrices, this capital X and capital X dot, using the data that we are given about this system. And the second step is like once we had this data x and x dot, the next step is actually the important step, where what we do is that then we construct this augmented library. And I guess our project was also about this construction of this augmented library that we have. And this is, I would say, this is the important step here, because the and I guess the SINDy algorithm actually depends on this construction of this library. And our actually project was also like constructing this library for the compact Riemannian manifolds. So the thing here is that this theta x is actually what captures the nonlinearity of our dynamical system. So once we have this data x and x dot, what we do is that now in this augmented library, we use these nonlinear functions. And the nonlinear functions can be anything, varying from these trigonometric functions, we can have the polynomial functions, or we can have the mix of different functions. And as I was saying, that our project is actually where we have constructed these actually these libraries using what I call as, these are the Kirchhoff library actually that we have constructed, that we were actually proposing to construct. And this construction of this library is where you have the freedom. Like usually that is where you have the freedom, like it depends on the physical system. So the construction of this library actually depends on the problem that you are dealing with. And actually I will show, while I will discuss the problems, I will show that for each problem I have chosen the library depending on the problem that I had. So that is actually what I will show as well. So the main step is actually this construction of the library. So once you have decided the library, since we have already constructed x and x dot, what we do is we evaluate these nonlinear functions that we have in the library. We evaluate all that x on those nonlinear functions. So that is actually the second step. Once we have this nonlinear library, what we do is then we actually convert that. Once we have this augmented library, now we convert this problem into the regression problem, where we have this x dot is what we have constructed earlier from the data. Then we have this augmented library. Then we have this matrix of sparse vectors. And the function of these sparse vectors is actually this choosing of which nonlinear functions do I need in order to represent this dynamical system. So this is where we have the sparse regression part here. So this sparse, that the vector, the matrix of these, the actually the matrix of these coefficient vectors, actually the coefficient vectors that we are selecting for choosing these nonlinear functions. So actually from data, now we are moving to this regression problem. And regression problem, it takes these nonlinear functions and these coefficients, choose which nonlinear functions do I need to represent this dynamical system, nonlinear dynamical system. So from here, what we do is that now we solve this sparse regression. Actually, in these slides, I haven't included the methods that we are using. Usually, we use the lasso regression, where we have what we do is that we use regression problem plus we use that hyperparameter term, so that we get sparse regression terms. Or what we use is another algorithm that we use is STLSQ, where we have the regression, that is actually the ordinary regression that we use. But after doing the regression step, then we use this thresholding step, where if our any of the coefficients is below the threshold, we make that as equal to 0. And these are the two regression techniques that we have been using in the SINDy's algorithm. So once we have solved this regression problem, then depending on those nonlinear functions that you have selected, you get that this xk dot, which is actually one of the equations that we have, that is represented as the linear combination of those nonlinear functions. And only those are chosen depending on that algorithm, or depending on the threshold that you have selected. What we get is we get that x dot is written as the linear combination of these nonlinear functions, and the nonlinear functions come from that augmented library that we have already constructed. And this one is actually the representation of what we are actually doing over the whole process. And as I named this one is actually the the simple SINDy actually. And what we are seeing here is on the left hand side in the red, you can see that we have r dot v dot, which is actually representation of those derivatives. And on the right, the first term that you are seeing, the first matrix, is actually the augmented library. And on the extreme right, this is the matrix representing those sparse coefficients. Meaning what we are doing is that we are solving this because on the right you can see that we have created this regression problem where what we are solving this system, and this is actually the representation of the lasso where we have this lambda is actually these parameters which are used so that we are selecting only those parameters which are above that regression. And this is actually the representation of the SINDy's algorithm. And in this algorithm, what you can see is that functions that I am selecting, like this 1, x, y, z, these are actually representation of the first degree polynomials. Then after that we have vx, vy, vz. These are not, first of all, these are not the derivatives here, because as we are discussing, this is the SINDy algorithm. So for the simple SINDy algorithm, I am not in the x that we have. It is just the function of the x. It is not the function of x dot here. So these vx, vy, vz, these actually represent different nonlinear functions. So these are not any kind of derivatives here. These are just the simple function, nonlinear functions that we are using in our augmented library. So this is actually the representation of the basic SINDy algorithm. What is actually SINDy algorithm doing here? And after that, so this is actually which gives you the idea about how this algorithm is working. And after that, these are actually the examples that we had constructed while working on this project. This is actually the example which is also present in the paper, the first paper of these SINDy algorithms. And in this paper, and in the paper that they had done, actually they had used a different code because they had done everything in the MATLAB, but we were actually working in the Python. So what we did is that we actually reconstructed those examples. So the first example is about the Lorentz system. This is the 3D Lorentz system, and we were trying to see whether we can replicate whether we can replicate these equations again. So the first equation, the fourth equation that you are seeing here, is the theoretical Lorentz system, and for this system we have sigma equals to 10, rho is 28, and the beta is 8 over 3. And the equation 5 is what SINDy identified. And in this system you can see that the sigma that we had as 10, that is actually same as the 10.0, and for this 28 we are getting 27.998, and about the beta, which is 8 over 3, we are almost getting the same 2.667. And this equation 5, as I was saying, that this is what SINDy, actually our algorithm, was identifying. And after that I have few figures like representing these x1s and x2s here, like x1, x2, like these are the trajectories for that Lorentz system. And what you can see is that actually our algorithm was able to capture the dynamics perfectly. And one thing to mention here is, and it's the same for the phase diagram. And in this case, what you can see is, after you can see like this xk is capturing the model, but it's not capturing exactly. And the thing is, this is because of the initial conditions. The initial conditions that I was selecting, this was around 0.5 and 0.5. But in the original paper, they were using 2.0 and 0, 2.0, 2. So the initial conditions for the paper that they had used, that is actually different from what I was using here. And I should, because in the paper they haven't actually mentioned that thing, that but this thing what I have seen is that it actually depends on the initial condition as well, because this is the chaotic system. So you have to be little careful about the initial condition that you are selecting for this system. So if you move away from the, I would say, the feasible initial condition, you might not get the same system. And one thing that I was saying about the library here, let me actually move to the system, this Lorentz system again. So what you can see is here is that x1, x2, and x3 is, these are just the linear polynomials here. So if you just see them as the polynomials in xk, what you can see is that these are the linear polynomials. And for my case, when I was selecting that, because as I told you that the SINDy algorithm, it depends on the augmented library that you select. For this case, when I was selecting the augmented library, I selected the polynomials which are having degree less or equal to 2, because we have this x1, x2 term as well. So that is why what you can see here is that you have like almost the exact coefficients that we have in the theoretical system, because again it depends on the threshold as well. Because when I selected the degree less or for the polynomials with the degree less or equal to 2, I selected that the coefficient, the threshold, should be such that I don't have those x1 square terms, x2 square terms. Those can be here, but it depends on the threshold at the end. So this is about these Lorentz system, and this is the true simulations and the model simulations, like that. This is what our SINDy algorithm was predicting. So this is about that one. So it was actually able to capture the dynamics. The second example is actually about the cubic, where we have this nonlinearity. So this is about the nonlinear damped oscillator, and now we have this nonlinearity here. And again, this equation 6 is the theoretical system that we constructed, and the example 7 that we have here is what was actually captured by the SINDy. And again, you can see the coefficients are somewhat similar to what we have from the theoretical system. So this was the algorithm was able to capture the dynamics. And in this case, again, if you talk about the library, again, because I already knew that the theoretical system is using the polynomial library, so I selected the polynomial library with the degree less or equal to 3. So that's how I was able to capture this x1 cube and x2 cube.
So I'm guessing that in equation 7 there, the bottom left coefficient is actually with a plus, right?
uh yeah, oh sorry, I had this minus
Yeah.
one. Yeah,
Yeah, yeah, no,
it's
no problem, no
actually,
problem.
yeah,
Just for
yeah,
clarification,
yeah,
but good, good.
yeah. And this is what was captured by our SINDy algorithm. And you can see it was actually able to capture the dynamics exactly. And same is for the phase diagram as well. It was able to capture that one as well. But again, and this is actually this, the thing is like in this case, what you can see is that I'm not adding any noise, because that is the first problem what I have seen with the SINDy. Either it is SINDy or the modified one that they call as the SINDy-PI. The issue is of the noise. Like if you add the noise, the algorithm is not able to capture the exact dynamics, and that is one of the drawbacks with the SINDy algorithm. And as I was saying that, obviously, like in most of the cases, what we have is this data x only, so we don't have the x data x dot. And what we do is, usually what we do is that we then calculate this x dot, and while calculating this x dot, usually that is where we get the noise in the x dot data. So in this equation 2 that we are using, so that's not actually the what we have exactly, like where we had this x dot is that augmented library times that coefficient matrix. Usually what we have is that x dot times that augmented library plus is this some noise. And in this case, what we are doing, because we were doing the experiments with this one, so we assume that this z is this iids from the Gaussian entries, but the mean is 0, but the we had the variance of eta. So that's how we added the noise to this x data, this x dot term. And then we have to solve this new equation actually, because this is the equation with the noise. And you can see like, we can see like up to, if you see the time up to around 12.5 or the 13, you can see that the algorithm is able to capture the dynamics clearly. But after that, you can see that it is actually varying from the actual dynamics. And that is that is the issue with this SINDy algorithm. Like if you add the noise, then it's not able to capture the dynamics. It is able to capture the dynamics, but only after the small amounts of time. Like that is what you will see in the SINDy-PI as well. So it is able to capture, but not for the longer times. Then that is why the like, and in the that is what I was calling the
We might have lost the audio. We lost Umair.
so that we can capture these the terms with this time derivative as well. So what we
Umair,
do
we
is,
lost
yeah,
you. We lost you for a few seconds. We don't see anymore your slides.
uh, I guess,
Yeah,
can you see it now?
yeah, yeah. No.
This, oh sorry, is this visible now?
Yes, very good.
Okay. So this is actually the SINDy-PI, which is actually the modification of the simple SINDy algorithm. And as I was saying, that we don't have the x dot term in the f that we had in any dynamical system, but the SINDy-PI is actually extension of the SINDy. And in this case, what we try to do is that in the augmented library that we have, we introduce actually the x dot term as well. And now what we do is we try to solve this system that is given in the equation 8. But the problem with this equation 8 is that usually the algorithm, what they try to do is that they try to make these quotient matrix as equal to 0. So usually what the algorithms do is that they try to get the trivial solution. But that's why actually we have the SINDy-PI. We don't just have the implicit thing. What they try to do is that the idea is that if we have, so to avoid those trivial solutions, what we do is we fix one of the components in our quotient matrix, and what we try to do is we actually remove one of those quotient matrix or the nonlinear functions which is actually containing that derivative. Then what we do is once we have removed, we try to solve the system of equation, this system given in the equation 9. And in the equation 9 we have this theta j is the column that we have removed from the augmented library, and this is minus times this augmented library, and while we have removed that this theta j containing that derivative. Now the thing is, like, what you can see now here is that in that augmented library we can have different number of these columns, and we are not pretty sure where is this x dot present. So that's why we have this SINDy-PI, this parallel and implicit. What we are trying to do is that we actually try to solve each, like, remove first column and then try to solve that system. Then for the second column, then we have different system and then solve that one. So that's why what we call as this parallel and implicit. We try to solve everything, and then we have these different number of systems, and out of those systems we actually select one where we have least number of these variables, and the system which is actually able to capture the exact dynamics. So the idea, that is actually the idea of the SINDy-PI. We try to select the system out of these parallel calculations. We select that system which has the least number of variables, and where we have these least number of variables, and the system which is able to capture the dynamics exactly. And the principle that they use is like in the SINDy-PI paper, if you go through the paper which I have given the reference as well, they say that actually the principle is that usually the system which has the least number of variables is actually the exact system as well. So that is how that is the idea behind the SINDy-PI algorithm. And this is what we have done, like the examples that we have constructed for the SINDy-PI algorithm. And this is the example actually that is not actually present in the paper that they have published, because this is the example that we have constructed on our own. And this is the example of this spherical pendulum. And for this spherical pendulum, the idea is like, now what we try to do is we try to capture this Lagrangian equations. So what we are trying to do is, if we will be able to capture the dynamics of a particle which is moving on the sphere, which is same as this spherical pendulum. And the potential here we are considering is the gravitational potential only. So the idea is, first of all, to construct the Lagrangian, and this Lagrangian is the difference between the kinetic energy and the potential energy. And the equation 10, this is actually the kinetic energy for the spherical pendulum, and the equation 11 is the potential energy, and the equation 12 is where we combine this T and V and we get the Lagrangian for this spherical pendulum. Now from this equation, now we will try to get our equations of motion using the Euler-Lagrange equations here. So, and this 13 and 14 actually represents these Euler-Lagrange equations. So again, the question is about which library do I need to select. Again, since I know that the equations here, these dynamical equations, these are governed by these trigonometric functions. So first of all, I will select the library containing the trigonometric functions. And one thing that we need to understand here is that we have this theta dot and phi dot here as well. So if we want to capture that, that is what I had done. Like, I actually, in the library, I included this theta dot, phi dot, and this cot theta as well. And once I introduce this term in our dynamic as well. So this was like uh, uh, after fixing the parameters, that keeping the radius as 1, m as 1, and g as 9.81. I haven't included the units here. Actually, these are like just the acceleration, mass, and the radius. And in the equation 15 and 16, that is what you can see the dynamics which was actually captured by the SINDy-PI algorithm that we had. And you can see it is almost exactly it is almost similar to the dynamical system. But the thing here is that is about this theta dot and p dot. And what you can see is that you have to give, like, for this system, in order to use these algorithms, you should have the idea about the equations. So you should have the idea actually about this library, which function should I include in the dynamical system. And what you can see is that these are the trajectories which were actually captured by this algorithm, and you can see like these are almost same. And same is for these Trinidad and identical systems, that you can see like this is the motion that was captured by the algorithm, and this is again, these are almost same. And then we have, after this, once we were actually pretty satisfied, like we can actually move forward, like we are able to capture some of this, because if you see this spherical pendulum, you can see that the particle is moving on the sphere, which is because sphere we can consider as a compact Riemannian manifold. So that is how we were motivated that we can move to the differential geometry. And here I am including some of the concepts about these smooth manifolds. And first one is like how to define the manifold, and for that manifold you have these open sets ui, and then you have these PIs, which are the homeomorphisms usually. And then we have these transition maps, which are actually, and the manifold, if you just want to understand what is the manifold in the simple language, it is like the curved surface, and locally that surface is uh, homeomorphic to a real space of dimension n, if the manifold is of dimension n. And then after that, we might, because we will be using this terminology while defining our library for the compact Riemann manifolds. Then we define the tangent space, and this tangent space we define as the velocity of these curves, these which are defined as the gamma. And we define for each curve which has the same velocity. That is how why we are getting this tilde here, which is actually the equivalent class of all curves having the velocity v. So that is how we construct the tangent space at any point. And the tangent space, it can be also defined through the concept of derivations. So the derivations are actually which are following actually these two rules, the linearity and the Leibniz rule, and that's how we define the D. So the derivations we can define through these tangent spaces through the derivations as well. Then after that, we define the smooth vector field. And the smooth vector field is actually for each point, what we are doing is we are for each field we are done. First of all, this Tm is actually the tangent bundle. So what we are doing is that we are taking the union of all of these tangent spaces, and that's how we define the tangent bundle. And then we define this smooth vector field for each point that we have. So once we have these, and then we define the Riemannian metric as well. And this Riemannian metric is kind of an inner product that we associate with this Riemannian manifold. And this metric, it has to be, and you might have seen these are the properties of those norms that we have seen, that this is the symmetry, and then we have this greater or equal, the norm has to be greater or equal to 0. And then we have, this is what we call as the positive definite property. And then we define the connection, and this connection is actually how we take the derivatives of the vector fields on those actually the Riemann manifolds. And this is how we define that mapping as well. And then we have these properties for that connection. Then we have what we call as the geodesic, and this geodesic on the manifold is similar to how we define as the curve which has the shortest distance between any 2 points. Like in the plane you might have seen the line, but for the curved manifolds these might be different curves. Like on the sphere we have those great circles which we call as the geodesics there. And in the last line what we have is this is the equation of the geodesic, and the equation that you can see, the gamma symbols that you are seeing, this gamma j I j k, these are the Christoffel symbols. And these, and the all the slides that I have explained about these differential manifolds, these differential geometry, this is all because I want to introduce these Christoffel symbols, because in our manifolds we have actually constructed the library using these Christoffel symbols. And from here, that is where we introduce this concept of these compact Riemann manifolds. What we have done is that we have actually constructed an example. So we have this torus, which we can consider as a compact Riemannian manifold in R3, but the metric that we are introducing is this, the metric tensor that you can see is this one, because if you introduce the matrix of dx square plus dy square, then it is not actually the embedding, then you might not consider it as a flat. Actually, that is the problem with the differential geometry. But with this metric, we are actually considering it as a compact manifold, and the embedding that we are giving is this x is r plus r cos phi cos theta. And what you can see is, if this embedding, you can see it as the parameterization that you might have seen for this torus as as a manifold in R3. And the metric tensor that we are introducing here is this r plus r cos phi 0 0 comma r square. And to get this metric, what we are doing actually here is that we are introducing r vector is x comma y comma z, and this r vector is the function of theta and phi. So first of all, what we do is we take dr over d theta, the partial derivative of that r with respect to theta, and then what we do is that we actually just take the inner product, and that is how we get this metric tensor here. And for that metric tensor, on one term for this metric tensor, the first row and first column, that is how, and this is which you will get by just taking the inner product of that r with derivative of r with respect to theta with r with respect to theta, and that's how you will get. And other terms, this 0 and 0 that you are getting, this is because the inner product of r with theta, and if you take the dot product with r, the derivative, partial derivative with respect to phi, you will get the 0. And that's how we are constructing this metric. And this metric is actually important, that is how, because that is which we will use in the construction of these Christoffel symbols. So from this metric, the tensor that we have here, now I have actually the components for this one. G theta, theta is the first term, this first row, first column term, and same for the G phi, phi that we have, and all other terms are 0 here. So once we have these, so here I have actually given this general construction for construction of this Lagrangian on any manifold. So for any manifold, if we have these qi's and qj's as well as the local coordinates, and the local coordinates I mean by, because for the Riemann manifold you don't have any coordinates, special coordinate system as you have in the Rn. So that is how we represent these qi's and qg's. And for that system, the kinetic energy is given by half of m times gij and qi dot and qj dot. Actually, this is the notation that you are seeing. This is actually the Einstein notations. So actually, you have to take the summation over I and g. And same for this potential. And here I am assuming that this potential is just the function of q. So it's actually the I would say this is actually coming from the conservative field. So that's why, like, this is not something like the friction or anything. So this is the Lagrangian, and again the definition for the Lagrangian is T minus E, and in this case T is this kinetic energy and V is our potential here. And the Euler-Lagrange equations are, that is how you actually get the equations of motion. So once you have this Lagrangian, so then you use the equation 18 to get the different kinds of equations, because in our torus, since we had theta and phi only, so we will have two equations, and for to get those equations of motion here, we will be using this equation 18. And this is actually the computation that I had done. So this is actually the different steps that we are using while constructing while actually constructing this example, this equation 18 from equation 17. So I am first of all using for the qi, then same for the qj. I am computing these different I am actually doing these different steps here. And what you can see is, because in these equations you have to use, in the last point that you might see, that I have to use the symmetrization trick, because that is how you get the equations of motion. And once you have these equations of motion, because I don't think I will go through the calculations again. So the final equation is this equation 19, and this is actually the general equation of motion for any particle which is actually moving on any manifold with the potential v. And this g that we have here is what I call as our this the metric tensor. But this glk that we have here, let me actually first, the stuff that you had, this glk that you are seeing here, this is actually the metric tensor. But this glk that you are seeing here, or here, this is actually the inverse of our that metric tensor. So this superscript is actually the notation for the inverse of the metric tensor, and the subscript notation is for our general metric tensor. And in this case, what you can see is in this equation 19, this term is the term that we're seeing here. That is actually important because you might have seen in when I was defining those defining the geodesic equation, this is what you might have seen. And in this case, that is what you are seing. So the equation, in order to represent the equation of motion on the Riemannian manifold, you have to use these Christoffel symbol. And that's what I have. I guess that was actually the trick in order to represent, in order to do the SINDy on these Riemannian manifolds. What I was doing is that I don't want to use all these terms here. So the best is like use the compact form of all these terms. So if I am able to capture these Christoffel symbols, obviously I am able to capture these terms as well. So that was actually the idea behind doing this project, actually, to move into this direction of doing this algorithm on these Riemannian manifolds. So what we were trying to do is that capture the dynamics using the library of the Christoffel symbols. So that is why these Christoffel symbols are important for us. So if I am now, for this V, if I am saying that the particle is moving on the torus but under gravity, so what I will do is that I will use the gravitational potential. And in this case, if I use that, that is how I get this equation 20 and equation 21. So now this is the theoretical equation. These are the theoretical equations of motion for the particle moving on the torus under gravity. So in this case, again, since we had the variables, these qi and qj are actually theta and phi. So in order to construct our in order to capture the dynamics in the customer library, what I did was that I introduced this product, like I introduced these terms here that you can see, this one like this and this. So what I was able to do was, once I introduced these libraries, are actually the functions, actually the nonlinear functions that we have. So this was this equation 22, and equation 23 is what was actually captured by the SINDy algorithm. And these are almost the same, that like these, not exactly same, but these are almost like the same thing, because now you can see from these simulations that we had done, these are the predicted and the actual velocities, actually not just the t and theta, these are actually the velocities as well. So you can see that our this algorithm was able to capture the dynamics. But again, the thing is about this library, because I have introduced the Christoffel symbols, and this is what was actually identified by the system. And in this case, what you can see is that I have used the same initial condition for training as well as for the simulations as well, and which is not the case in most of the examples that I had did. And the problem again is with the noise. In the If I introduce, as we discussed in the SINDy algorithm, the same issue is with the SINDy-PI as well. So if you add the noise in the SINDy-PI, what we can see is that if you add the noise, the algorithm is able to capture the dynamics, but only up to the small times. Like you can see in the uh, on the panel on the left, you can see up to t equals to 1, you are able to capture the exact dynamics, but after that is actually is not able to capture the actual dynamics. Same is with this theta as well. So if you move after 1, you are not able to capture the exact dynamics, and that is the issue with this SINDy-PI. And I guess our next step is like creating the algorithm which would be robust actually to these small noises as well. And you can see, like if I add the noise, that is the issue, like we are not actually getting the exact system, and that is the problem with this SINDy-PI as well. And I guess that is actually the big project, actually, like trying to identify. There are actually few papers which I have seen. There is one paper where they have tried to, not for the compact manifolds, they have used it just in Rn. But the thing is, like what they were trying to do is they were trying to capture the Lagrangian. But the only modification that they had done to this algorithm was that they changed the optimization, like the method that they were using. Like they moved from lasso, they moved to STLSQ. But in this case, I feel like that you don't have, like, because we have used different both STLSQ and lasso, but it is not actually able to uh, capture the dynamics in presence of the noise. So I guess we have to use different steps. And what I am feeling now is that because this SINDy-PI is not able to capture the dynamics in presence of noise, so I feel like that we might have to use the regression on for these compact manifolds. I feel like that we might have to use the regression on the compact manifolds, because the issue is that if you have the data on the manifolds, when you are trying to do the regression, you are not taking in account the curvature of this manifold. I guess that would be the next step, where what we have to do is that introduce that introduce do the regression on the manifolds, and then try to move back so as to capture the dynamics. But there is one more issue as well, is that if you move from, like, because the regression that we are doing is in the Rn, and this manifold that you have, this is the curved space. The problem is that you can move to the tangent space and do the regression there. The issue is that if you move back, you cannot actually capture everything, because you have some points on the tangent plane and some on, because that's why we are using the compact thing here, because you can move from tangent space to the manifold, and from manifold to the tangent space using logarithmic functions and exponential functions. The issue is that when you have moved from point to the tangent plane, you might not be able to go back to the compact manifold, because you cannot measure the distances on the manifold. So that is how like we are actually looking for other directions as well. But this is the first step that we might do, that doing the regression on the manifold, that is might be the first step. And I guess, yeah, that's it. And these are the references. The first one is the basic SINDy paper. The next one is where they have introduced the SINDy-PI. The third one is actually where I have got that the figure path is SINDy, and the fourth one is our paper, which is actually in the preparation. That is where we are working on. And I guess that's it. Thank you.
All right, so thank you very much, Umair, for the great presentation. So maybe I'm gonna ask one question and leave the others for
Yeah,
offline. So my question is this: so do you, have a way to using this method to actually, I'll ask this other one. So, when you have a compact manifold, right, you have the possibility of recurrence. Okay, let's think about the circle.
yeah,
So you might have periodic orbit or something like that, right?
yeah,
So now, on a line, right, linear space, right, that's less likely. You have to have a way to go back and forth and so on. You have to pass critical, more different things, right? So what I'm
yeah,
saying is that if you have a certain sampling at a certain rate, right, uh, on a line, you're going to have a sparse sampling because you keep sampling at different points.
yeah,
Well, on a manifold, let's say in the circle, you keep having denser and denser, unless you are sampling in the period, the multiple of period, or you're gonna get a dense sampling, right? So on a
yeah,
compact manifold, you're gonna have some advantages, right? Because
yeah,
for identifying the nonlinearity, because the nonlinearity is going to be defined in the circle, and you have a dense, basically most likely a dense set of points available, right? A denser set of points available on the line. So expect that this should have a positive effect on the identification of the dynamics, right?
yeah. And I guess, like, if we have the data on, like, if we have the dense data, like, because I guess that is why I am using the compact Riemannian manifolds. I am not going for the general manifolds, because for the general, I don't know what will happen after, like, after few, like, because we don't, because for the, as you were saying, I guess that's the right point here. Like, if you have this compact manifolds, obviously this is the finite manifolds. Obviously the particle might come back to the, like, the original position. I guess, yeah, that is the point that I am using that's why I am, like, moving only for the compact RAM, these compact Riemann manifolds.
Good. So very good. So thank you very much for the presentation. It was great to have you here. So thank you again.